Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, these days we are discussing the space plasma environment and its effects on the orbital spacecrafts. So, in the last session we discussed what is the genesis or the origin of the space plasma in different Earth's orbit, and we discussed that the main origin of the space plasma is the solar wind, and we and already you know that we discussed in the first module, that is the solar wind, and whenever there is the solar activity or the solar maximum or even in terms of solar cycle, then this solar wind it becomes the solar storms, where a very energetic charged particles as well as the radiation it comes in the form of solar flare or the coronal mass ejection or solar energetic particle events. So, this is one source. The other source is the terrestrial source, that is the ionosphere. Again in the ionosphere, the particles are charged or ionized by the radiation from the sun, basically the UV radiation and the X-ray. And we discussed that is those the charges in the ionosphere they couple to the magnetosphere, and that process we named that process as the ionospheric outflow, and because of that we get a plasmasphere. Then there is the radiation belt. So, all these things we discussed, that how this what is the nature of the space environment. Then we discussed what are the effects of those plasma environment on the spacecraft. So, the profound effect is the spacecraft charging, and whenever the charged particles have higher energies, when it is in the some tens of kilo electron volt, it can give rise to the differential charging, and differential charging means there can be electrostatic discharge. Differential charging means 2 parts of the spacecraft will acquire different potential, and the potential difference may be so high, it can give rise to the breakdown of the dielectric or the surface material. So, this gives rise to the arcing and those type of phenomena. This is one of the very profound phenomena, and this happens generally that higher Earth orbit, especially the geosynchronous or geostationary Earth orbit. It may happen in medium Earth orbit also. Then the other effect we discussed, that is the electromagnetic interference, and that we will discuss of course more in detail, but just to mention that this plasma environment also create the electromagnetic interference, which can disturb the that wireless communication. Meaning that the satellite communication, navigation, and even it can disrupt the sensitive electronic instruments. Then we discussed the some thermal effects, and especially one is the atmospheric, the drag. So, especially this can happen in the low Earth orbit, when there is a geomagnetic field, where the geomagnetic field is relatively stronger, and if you have a charged spacecraft which is moving in that magnetic field. So, this gives the Lorentz force, and this gives rise to drag on the force. So, this becomes challenging for the attitude in the orbit control system for the station keeping of the spacecraft. And then we also of course, this year we defined the low Earth orbit, what is the plasma nature. So, we have seen that in low Earth orbit the plasma density is high, but the energy is less. It is something let us say less than 1 electron volt. Of course, it is again a function of the space weather or the solar cycle. In normal weather, it is very the plasma is called the cold, whereas in higher Earth orbit, in geosynchronous or geostationary Earth orbit or the medium Earth orbit, there can be that is the electrons can have higher energy, especially during the geomagnetic storm. So, we have seen that what are the the effects and the satellite operational effects and different orbits. We discussed a little bit in more detail. So, we will continue today with the effect. We will take the spacecraft charging, that as I said, this is a profound, that is the effect of the plasma environment. So, in this topic spacecraft charging, we will just see, that is how we can, from the very fundamental thing, charging means charging of a capacitor, how I can relate the spacecraft with the capacitor charging, and to derive or to build up the fundamental theory of the spacecraft charging. So, in this regard we will discuss the probe theory, and probe theory means that is it is called the Langmuir probe. So, we will also discuss the Langmuir probe, and then we will discuss the physics of spacecraft charging, and we will show that is a spacecraft is nothing but a probe. And when I consider it is like a probe, then how it collects the current and what is that, how the potential is built up, all these things we will be able to understand. So, what is spacecraft charging? Already I said in my last session, that is it is a natural process. Whenever you put a probe in a charge environment, charge will get accumulated on the surface. So, you can consider the spacecraft as a probe which is moving in a, or which is there in this plasma environment. So, basically it will collect the charges, or it will get accumulated those charged particles from the ambient plasma environment. So, it can be on the surface or it can reach to the interior. Surface means when the energy is not very high, then it can give rise to a surface charging, but when the energy is so high, that is those charged plasma, it can penetrate the surface and it can go interior to the spacecraft. We will see, we will discuss what are the different types of spacecraft charging, then we will discuss this topic in more detail. So, whenever a spacecraft has a net charge, so it can be positive or negative. So, whenever there is a net charge, whenever it is not a neutral environment, what is the result? The result is that it will create some electric field intensity or some the electric energy or the potential energy. So, so that you can say this is by the Gauss's law. So, whenever the Gauss's law means it is the relation between the electric field so it is relating the charge in the electric field intensity. So, whenever there is some charge, whether it is positive or negative, it will give rise to the electric field, means the environment is not neutral. Surrounding the spacecraft, the environment is non-neutral. And whatever we discussed in the last class, last class, that is the device shielding or device length, the same thing is valid here. We will see here, that is a spacecraft, surrounding the spacecraft there is a shield or the sheath formation, and it will have some device length or the device radius. So, the electrons and the electrons and ions of energies up to about few tens of kilo electron volts, they are very important players in the spacecraft charging. So, in this case it can have the spacecraft surface charging. We will see in more detail in subsequent sessions, that is how to model the spacecraft surface charging. Of course, when it goes to hundreds of kilo electron volts, it can give rise to the internal charging also. It will not restrict itself to the surface, but it can penetrate to the spacecraft dielectric. It can be the dielectric associated with the circuit, or it can be a thermal control system or thermal insulator. We will see all those things. So, as we said when we are discussing the plasma properties, so the plasma as a whole collectively they are neutral, and the plasma densities it will fluctuate, because it is very much temporal, and it depends on the the solar wind condition or the space weather, whether it is the ionospheric the charge density or the charge density or the particle density in the orbits, it fluctuates very much, because the solar or the space weather, it is having a the short time scale behavior. So, here the time scale again it depends on the plasma frequencies, as we have seen. If there is some instabilities or there is some local instabilities, so this gives rise to the plasma oscillations. Okay. But when we will consider the spacecraft, the charging or the spacecraft velocity potential, that process will be much slower, that is the individual fluctuations of the short time scale fluctuations of the plasma. So, what I mean to say that spacecraft charging, it takes longer time than the ambient plasma fluctuation, because it takes time to fill up the capacitors. So, we will consider the spacecraft itself like a capacitor. So, whenever you are to charge a capacitor, there is a time constant. So, it cannot be charged instantaneously. So, it will depend on the damping, how. So, it is called the RC time constant, RC time constant. So, in a circuit it will depend what is the the value of RC, whether the charging will be faster or slower, but it takes the finite time. So, now since we have called that it is a capacitor, let us see how the satellite I can represent it like a electrical capacitor. So, what is a capacitor? Capacitor basically it means there are two metallic plates. So, it can be parallel plates, it can be spherical plates, a spherical the configuration, or it can be the cylindrical configurations. So, you need two plates. So, here one plate is the spacecraft surface. So, it is the conductive plates. So, this is the your capacitor, parallel plate capacitor, two plates, they are separated by the dielectric. So, dielectric can be free space, or it can have some dielectric with finite dielectric constant. And the surrounding plasma, it will serve as the other plate or the reference plate, where we will consider the potential is 0. We will do this in our subsequent when we do the mathematical modeling. So, you can consider it as a capacitance formed between the plasma and the capacitor. So, one plate is your spacecraft surface and the other plate is the plasma, the non-neutral plasma. Non-neutral plasma means outside the Debye length or the Debye shield. So, here the vacuum or the thin plasma sheath, whatever I said, between them function as the dielectric medium. So, this dielectric medium, it will be that whatever the because in between the non-neutral region, or that is the charged spacecraft, and between the plasma, the neutral plasma, there is the plasma sheath. So, that you can consider the space between these two plates. So, this basically it forms a capacitor. So, these are the three configuration, as I already told you. So, the capacitance C between the spacecraft and the ambient plasma, it can be estimated using this formula. So, this is a very standard formula, where epsilon 0 is the vacuum permittivity or permittivity in sphere space, A is the area of the spacecraft surface, and D is the effective distance between the spacecraft surface and the plasma. Plasma means the neutral plasma, where the potential is 0. So, and this D is, it is, you can approximate it by the Debye length, and you know what is Debye length, already we derived and we described what is the Debye length. So, this model, it aids in understanding how spacecraft accumulate charge over time and how they might discharge, potentially leading to electrostatic discharge or ESD. And we will see that this ESD can affect the onboard systems. Now, we will just see what is a capacitance charging. So, if there is a steady ambient current I, the time tau for charging a surface is given by tau I is equal to C phi. So, basically what is tau I? It is basically the charge, because dq by dt or q by tau is I. So, I can write like that. So, this is capacitance multiplied by the potential. So, C is the capacitance, phi is the surface potential. So, just for a simple example, the surface capacitance C of a spherical object of radius r is equal to 1. So, where it is given by epsilon 0 4 pi r. So, it will be 10 to the power minus 10 farad per meter. So, now let us take the ambient current is equal to I is equal to j pi r square, where j is the ambient the plasma flux or effluence also you can say. So, the object in the space environment of a flux density, if you consider j is equal to the flux is 0.5 nano ampere per centimeter square, then it would charge from 0 to 1 kilovolt in tau is equal to 2 millisecond. You can calculate it. So, which you can show, you can calculate what is C, and then you can substitute it for r is equal to 1 meter using this expression, then you can show it the tau is 2 millisecond. So, which you can show is very large as compared to the plasma fluctuation given by the plasma frequency. So, you can calculate the plasma frequency when you know what is the plasma density and the charge. So, you can use that formula for plasma frequency, and you can calculate what is the plasma period, and then you will see that this is much larger as compared to the plasma time scale. So, the charging time tau it increases directly with the charging level phi, and it is inversely with the radius r and the current density j. So, this is clear from these expressions. Yeah. So, I can write tau is equal to phi by r j. So, capacitance charges is analogous, another way I can we shall explain it. It is filling of a tub with water. So, the water flow rate and the hose size, that is the cross section of flow, control the time of filling. We will just see this from the next slide. So, during filling the water level will rise, therefore, incoming current exceeds the outgoing current. We will just see, it will be clear when we explain the whatever the cartoon we used in the next slide. So, how the steady potential is built up, we will just explain. So, you consider here it is a tub and we are filling the water from a tap. So, this water is something like you can consider it as the plasma flux or current, and then you can consider this area of this or the way or the area of this tub is the is C, area is C, and its level, that is the height by phi. Okay. So, what will happen whenever it is filling the water, means you are charging it. Charging means what we understand by the charging, that its potential is increasing. Here the level is increasing. So, whenever this water is filled up, this will increase, slowly it will increase. So, this we can I can call it the charging process. So, the water flux J received in a period of tau, this equals a volume of water given by C into phi. So, that whatever the expression we showed it in the previous, this is the tau into I is equal to C phi. So, you see this is the volume, the area I am taking as C and I am taking the level height by phi. So, what will be the that is the total water, that is the volume of water it has accumulated, it is something like the charge accumulation, it will be given by C into phi, and this level will change with the time. Whenever you are filling it, it will change as water will the flow it will continues to flow it, the water flow will be continued, the level will rise. Now, you assume that you have put a small the outlet, you have put a small outlet, then what will happen? Then there is water is coming and then it is going out also. Now, when this incoming the rate, incoming this water flow and the outgoing water flow, this rate is the same, then what will happen? This height will not change. So, that will this concept will used in our subsequent discussions. This is something like the Kirchhoff's current law. So, in a junction current is coming. So, whatever the quantity of current is coming, it can be from different branches, current. So, all the incoming, if I1, I2, suppose if I go it is I2, then this incoming I 1 plus I 2, this is 3, I 1 plus I 2 will be equal to I 3. So, this is we will see here, just we are considering here two components. We will see that in spacecraft charging there are multiple incoming and the outgoing currents from the spacecraft. So, this condition is called the equilibrium, when the incoming and the outgoing the rate are the same. So, this is called the at the equilibrium we will see that this potential or the level is here, in this case it is the level of the water in the tub, they are constant. So, as I said that is the Kirchhoff's this is called KCL, Kirchhoff's current law. So, this is a steady state current balance, but this is not applicable when it is charging. So, when the potential is increasing, so there this Kirchhoff's current law you cannot apply, only when you can apply it when it is incoming and ingoing, that rate are the same, then only it is, otherwise that this potential you can find it in for the capacitor, the potential will be a function of time. So, once the tub is filled, the water level remains constant and therefore, the incoming and outgoing currents they balance each other. So, the current balance equation is not applicable for our example during the first 2 milliseconds. Just we have found that earlier we have found that is the charging time, it takes 2 milliseconds. So, within 2 milliseconds when it is charging, you cannot apply the current balance equation, but you can apply it thereafter when the balance is obtained, which is when the ingoing and the outgoing current balances each other, then I can apply the current balance theory. So, it can be noted that it takes infinite time to charge capacitance asymptotically, because if you see that formula, the V 0 1 minus e to the power t by tau. So, the t will take infinite time. So, this formula what I want to say, that V t is equal to V 0 1 minus e to the power minus t by tau. So, here we are considering the case of charging. So, a capacitor will take infinite time to charge to a voltage V 0. Similarly, if it is to discharge from B 0 to 0, it will take again infinite time, and the expression will be V t is equal to B 0 e to the power minus t by tau. Here tau is the time constant equal to RC. Generally, the charging and discharging will happen through a resistor. So, it again depends on what is the the material. We will see it that this charging and then discharging, it again depends on what is the type of the material, what is the dielectric we are using. So, depending on all these things, this will depend. Now, let us see how the spacecraft charging occurs. So, it occurs because of the difference between the ambient electron and the ion fluxes. This is very important here. It will be clear when we discuss more. So, what happens here, the electrons are faster than all kinds of ions because of their mass difference. So, if you insert any object in a neutral plasma, then it will collect charges. It is very, whenever you are inserting any probe in a charge gas or the plasma, it will collect charges, and the probe which can collect charges we will see that in a plasma chamber. So, that we will explain with the Langmuir probe, that is called the Langmuir probe. So, what is Langmuir probe? So, Langmuir probe, it is a the diagnostic instrument used in plasma physics to measure the key properties of plasma, such as electron temperature, electron density, or this built up electric potential. And why the name Langmuir? It is after the name of the Nobel laureate Erwin Langmuir, who coined the term even the plasma, and he only made this this probe or invented this probe, and it is named after him. So, it is a fundamental tool for analyzing plasma behavior in both laboratory and the space environments, and it can determine the electron temperature, then electron density and the ion density of the plasma by obtaining its current voltage characteristics in the characteristic curve depends on these plasma parameters. And it is used on board scientific instruments of the satellite, and its objective is to determine the parameters of the plasma in the upper regions of the Earth's atmosphere. So, very Langmuir probes are used as instrument in various when you want to study the space weather, Langmuir probes is a very important instrument. So, it consists of a sticking a wire into a plasma and measuring the current to it at various applied voltages. So, just we will see it now. So, a typical Langmuir probe consists of a small electrode, it can be a thin wire or a metal strip that is inserted into the plasma, and then when the voltage is varying, so from negative to positive voltage to the measuring the, then the resulting current is measured, and this curve, that is the IV characteristic, it gives various insights into the plasma's properties. So, this is that so here you see this is the probe. So, this one is the probe and it is inserted in the plasma, it is a plasma chamber, and then there is a voltage source, and there here is an emitter to measure the current. So, the voltage is you can change it. So, whenever you change the voltage from from the negative to positive voltages, so what you will see that this the current will this probe since it is when it is negative, suppose the potential is negative. So, it will attract the positive charges, and then we will see that curve, and it will be more clear when we see that. So, in the curve we will see there are three regions. One is the ion saturation region. So, at highly negative voltages the probe collects ions, as I already said, and the current remains relatively constant, allowing for the determination of the ion density. So, from that region of the curve you can determine the ion density. Then the transition region. So, after that, from the very negative voltage you are increasing the voltage, and the electrons will acquire the sufficient energy and overcome the potential barrier and reach the probe, enabling the calculation of the electron temperature and density. So, this you can calculate from the transition region, and there is a we will find that another region, that is called the electron saturation region. So, at positive voltages the probe draws electrons from the plasma, and the current it plateaus, means it becomes saturated, and then you can calculate the electron density from there. So, this is the three regions, as I said. So, this is the ion saturation region, it is when the voltage is negative. So, this is the negative voltage, and this is you are applying the positive voltage, and then this is the transition region when it is going from, and this is called the floating voltage, this is the plasma voltage, and then this is the transition region, and then it will slowly it will saturate. So, from these three regions, as I said, this all the parameters you can say. So, this Bf is the floating potential and Bp is the plasma potential, and analyzing this IV curve, there the researchers they can deduce various plasma parameters, including the electron, that is energy distributions, and the plasma potential. Okay. Now, we will quickly discuss, that is how the spacecraft charging happens. As I already said, it is because of the the speed difference, or the kinetic that is the not kinetic energy, it is the velocity difference, the mass difference of the proton and ion and electron. So, this gives rise to so, if I consider spacecraft as a Langmuir probe, so spectrum in the ionosphere or the magnetosphere, it may be regarded as very similar to the Langmuir probe in a laboratory plasma. So, the laboratory probe, it is not isolated in the same way as the spacecraft. So, in the laboratory probe, what we are doing, we are applying the voltage, and then we are measuring the, or we are monitoring the current. But here the spacecraft, it is no potential is applied. So, what it is doing, you are getting the current in response of the the whatever the plasma, or whatever the plasma particles is collected by the spacecraft from its plasma environment. So, if one knows all the current components, one can calculate the potential. So, thus the currents are here the driving force here, not the potential as in the laboratory based instrument. So, here as I already said, the electrons are moving faster than the ion, and what will happen, electrons will move faster, and then they will sit on the or they will be collected by the spacecraft surfaces, and then those electrons, whenever it is collected by they will start repelling the electrons, and they will start collecting or attracting the positive ions. But here what happens, let us consider this is the case of an the hydrogen atom, where this ion mass is 1837 times that of the mass of the electron. So, which gives you the if the thermal energy, that in terms of the kinetic energy, if you calculate this, if you put this, then you can show that the velocity of the electron is much higher than the velocity of the ion. So, it takes finite time to charge the surface because of the capacitance is finite. So, for typical surfaces at geosynchronous altitude, it can take a few milliseconds to come to a charging equilibrium. So, we will discuss more. So, this is just we are trying to build up the concept how we will analyze the that is how a spacecraft is charged. So, we will discuss more, and we will consider the different the types of the plasma and what are the different phenomena happens in our subsequent classes. Thank you very much.